This is an alternative to the method I showed you in Chapter 30, Part 1. The algebraic method from Part 1 works okay as long as you have polynomials, but if you've got other things, then you might ought to reconsider. So here's what we're going to do. We're going to literally compute these coefficients, f prime, f double prime, f triple prime, and then use the Taylor formula that we learned back in Calculus 2. And here's an outline of the method on a sheet that might be useful, say, for a notebook. Now I'll show you how the Taylor series method works using this second order equation. And notice here that our coefficient is a transcendental function instead of a polynomial, which would make the algebraic method quite difficult. So also notice from what we talked about in Part 2 that the coefficient of the second derivative is a 1, and 1 is never equal to 0. Therefore, we have all ordinary points. This can be expanded about any value whatsoever. And so step number 1 is to solve for the y double prime, which we'll do. Step number 2 is to decide what point we want to expand about. If you heard what I just said a minute ago, we can expand about any number whatsoever because there are no singular points for this. And all that this is saying is you need to come out with two constants in your solution. Doesn't matter what you call them, we'll just refer to them as a sub 0 and a sub 1. So we're going to expand about x equals 0. That'll make our calculation somewhat easier. And the two constants will just be a0 and a1. And so we take our second derivative that we just solved for. In place of the x in the second derivative, that's here, in place of the x, we want to use a 0. In place of the y, we want to use a 0. So we end up with y double prime of 0 equals negative a 0. Now we're going to make us a table and we'll list what we've got so far. And you see here in step 4, we're just going to continue repeating what we just did. So to do the third derivative, we will take the second derivative and do the derivative of that. Then we will make the substitutions. Now again, we're expanding about 0. So all the x's we will substitute as 0. In place of the y, that's what we decided in the beginning, we'll use an a0. In place of the y prime, that's what we decided in the beginning, we're going to use an a1. So making those substitutions, here's what we come out with. And then simplifying that and adding that to our list. And then doing the next derivative. So if we do the fourth derivative, I won't go through all the details of doing the fourth derivative. Again, we will do what we just did. All of the x's we will substitute a 0 for. For the y, we substitute a0. For the y prime, we substitute a1. For the y double prime, we substitute a negative a0. Now, as you can see, doing these derivatives is getting to be quite a chore. What I suggest is instead of continuing to do derivatives by hand, we utilize our Ch30. Now on the Ch30, what we're going to do is, this is our second derivative. That's what we started out with. Y double prime equals negative cosine of x times y. And we're on the fifth derivative, so we need to do the third derivative of the second derivative. That gets us our fifth derivative. So here's how we go about typing that. Now the 3 right here after the x is what tells it we want the third derivative. Now this is just where we're expanding about x equals 0. So we're doing the third derivative at x equals 0. So on the Ch30, we get the third derivative at x equals 0, which is right here. And that says 3 times y prime minus y triple prime. And then we want to substitute in place of the y prime and a1, and in place of the y triple prime, a negative a1. And so here's what we get when we substitute those. And we'll add that to our list and keep it going. Now the neat thing about doing this on the Ch30 is we can take what we just typed, change the 3 to a 4, and we've got the answer. Substitute our values and simplify. Add that to our list. And again, if we take our Ch30, where we had a 4 in the previous problem, we change that to a 5, press enter, and we've got our next answer. And we'll add that to our list. Now we're going to need to take our format for our Taylor polynomial and substitute. The f of x naught that we have here is nothing more than the y0. The f prime of x naught is nothing more than the y prime of 0. Now x naught is a 0, so x minus x naught comes out to be just an x. So again, we plug all of these in, and this is what we come up with. Now what we mean by writing this in standard form is we want to collect all of the terms that have an a naught in them together into a single term, and then all the other terms, which will have a1s, we'll write as a separate term. So we have this written as 2 terms, a naught times some polynomial, a1 times some polynomial. That's what standard form is. Now lastly, we would like to be able to write this as some known functions. And sometimes that is possible. And that means our knowledge of series, can we take this and write it as something like, maybe this is a sine of 2x, or maybe it's an e to the 5x, maybe it's a ln of x minus 1, I don't know. If we can write this as some known function, we would like to do such a thing. However, what we have here is a plausible solution. And in this case, there isn't a function that this writes as.